All right, in this video, I am going to do a couple of the problems from the Module 10 homework. The first one I have here is the problem number 37 from section 4.3. And here we are told that a wave of wavelength lambda traveling in deep water has speed v given for positive constants c and k by this formula right here. And the question is, does the wave have a min or a max velocity? And if so, what is that velocity? So let's go ahead and look at this problem. Let me pick a different color. And in order to find out if a function has a minimum or maximum value, one thing that we can do is find the critical points for the function by taking the first derivative and setting that first derivative equal to 0. And so we'll start by doing that. And in order to do that, I'm going to rewrite the function. So I have, sorry about that, I have v equals k times lambda over c plus c over lambda raised to the 1/2. And I write it like that so it makes it more straightforward to me that I'm going to use the power rule here. And then I'm looking for actually d lambda because lambda is my input variable. So I'm going to take the derivative of both sides with respect to lambda. And so I'll start that. Now I'll pick another color. So here we go. So v prime is, the k is constant, so I don't do anything with the k. Then I apply the power rule to this term right here, and I pull the 1/2 to the front. It leaves me lambda over c plus c over lambda. And then I subtract 1 from the power, so it gives me to the negative 1/2. Okay, so now I have this right here, but I'm not quite done because when I use the power rule, the base of my power, the base of my exponential term here is not just simply lambda, it's actually a function in its own right. And so I have to now apply the chain rule. So what I need to do is I need to take the derivative of that inside part. So I'll just write it like this for now. Lambda over c plus c over lambda, and take the derivative of that. Okay, so now come down here and I'll finish this off. The derivative of the velocity is k over 2 times, oops, I'm sorry, this should be a negative 1/2 because 1/2 minus 1 is negative 1/2. So that's, and I'm going to just go ahead and write that now this way as 1 over the square root of lambda over c plus c over lambda. And then that is all times by this term here, which is the derivative of lambda over c is simply 1 over c. And then I subtract from that the derivative of c over lambda. Now I'm going to come up here to this side just so you can remember what that means. C over lambda is equal to c times lambda to the negative 1. So when I take the derivative of that, I am going to have, instead of plus here, I'm going to have minus because I'll bring down this negative 1 to the front. So I'll have negative c, oops, let me go back to my pen. I will get negative c times, let me do this up here just so you can see it here. So if I take the derivative of c lambda to negative 1, that gives me negative c lambda to the negative 2, which is the same thing as negative c over lambda squared. So it's all my scratch work, so it doesn't come down here in my equals sign in my actual equation. So I'm having this minus c over lambda squared. All right, so hopefully that all made sense there. It was a little side thing I did here just to show what the derivative of that was. All right, now I know that I'm looking for when will this be equal to 0? And so the first thing I'm going to do is just kind of look at the function overall. And I'm going to do that with yet again another color. But let me point here. First of all, I know this term here is always positive because k is a positive value. So this term here is always positive. All right. This term here, I can rewrite that lambda over c. If I multiply the numerator and denominator of this term by lambda and this term by c, then I would get lambda squared plus c squared all over c lambda. And when I look at that, I say, okay, look, this denominator is positive as long as lambda is greater than 0, because c is always a positive term. Well, first of all, if we go back and look at the situation here, it's a wave of wavelength lambda. So of course, lambda is always going to be positive. We can't have negative wavelengths. So the denominator will always be positive. And then when I look up here, when I take two square terms and add them together, that will always be positive too. By 2 I mean as well. That's always positive as well. So this first term here is always positive. The second term here is always positive. So now everything then is determined by this term here. So I'm going to go ahead and rewrite that with common denominator. So I'll multiply this by lambda squared over lambda squared, multiply this by c over c, and that term would become, sorry, lambda squared minus c squared, all over c lambda squared. Again, this denominator is always positive. So now what we're really looking at here is this term right here, lambda squared minus c squared, and that is going to be positive whenever is positive when lambda is greater than c. It's 0, right? We can see that this numerator here is 0 when lambda equals c, because then c squared minus c squared would be 0. If this term becomes 0, the whole derivative becomes 0, and so now we've found our critical point. So I say therefore, we have a critical point at lambda equals c. All right, and so let's go ahead now and look at what's going on. When lambda equals c, that's my critical point. And I know that the derivative is positive. We just found that out up here. The derivative is positive whenever lambda is greater than c. So over on this side, my function is increasing because lambda is positive. I'm sorry, because the derivative is positive because lambda is greater than c. But when I go back and look at this again, I see that, oh, if lambda is less than c, I'd get some number that's less than c squared minus c squared. That would be a negative number. And so as long as lambda is less than c, my derivative is negative, which means that when lambda equals c, my function v is minimum. That's the minimum That's where the minimum value occurs. But now the next question is, it says, does the wave have a minimum or maximum velocity? Yes, it has a minimum velocity, and that occurs when lambda is equal to c. But the next question says, if so, what is that minimum velocity? So now what we have to do is go back up here to our original function for velocity and evaluate that function when lambda is equal to c. So then I have k times c over c plus c over c, which is 2k. So my minimum velocity occurs when lambda equals c and is equal to 2k. So that is my minimum velocity, and that occurs when lambda equals c. All right, let's see if I have time to put the next problem up here on this video as well, and that's going to be problem 4.3, number 39. So I'll go back here, 4.3, number 39, and this one says a woman pulls a sled together with its load that has a mass of m kilograms, okay? M is a variable. That's the mass of the load together with the sled. If her arm makes an angle of theta with her body, and you're assuming her body's vertical, she's standing up, so angle of arm to body is theta. And the coefficient of friction, which is a positive constant, is mu. So the coefficient of friction is mu, okay? The least force, F, so least force is F, that she must exert to move the sled. So I'm going to write that out a little bit more. Least force needed to move sled, that's F. Okay, and F is defined as F equals mg mu all over sine theta plus mu cosine theta. Okay, so remember m is the mass, theta is the angle of her arm, and mu is that coefficient of friction. And so we're looking for, tells us if mu equals 0.15, find the maximum and minimum values for F. Find max and min for F on the interval 0 less than or equal to theta less than or equal to pi over 2, and give your answers as multiples of mg. Okay, so we're going to be looking like, is the answer the maximum force 2 mgs? Is it 0.5 mgs? Is the minimum force 1 mg, or 0.2 mgs? That's what it means to give your answer in multiples of mg. All right, so let's look at this one. And we will start again. I always like to rewrite my function into something that is more easy for me to see how to differentiate. So I'm going to start by saying F is equal to, and I'm going to go ahead and substitute in the 0.15 for mu as I rewrite this. So I will have, rewriting the numerator is 0.15 mg. then I'm going to take this denominator and raise it. Instead of having it as the denominator, I'm going to write it as a term that I'm multiplying by. Oops, and I said I was going to put in the 0.15 here. Okay, it's a term that I'm going to multiply by raised to the -1 power. That's the same thing as dividing by that term. And I do that because now I can see I'm going to use the power rule and the chain rule side by side. So I get f prime is 0.15 mg. I bring down the -1, and then I have sine theta plus 0.15 cosine theta to the -2. And now I'm going to take the derivative of the inner term. Remember, the inner term is this term right here. So I'm going to take the derivative of that and make sure you put brackets or parentheses or something so you remember that this is all one term. Sine of theta, the derivative of the sine of theta is cosine theta. And then the derivative of the cosine is negative sine, so I'd have minus 0.15 sine theta. I think I got that all squeezed in there. Okay. All right, now I'm going to rewrite it so it's a little nicer for me. So I have f prime equals this -1 gives me negative 0.15 mg. And then the next term tells me that I have sine theta plus 0.15 cosine theta, that whole quantity squared as a denominator. And then in my numerator, I still have this whole term over here. So that is b multiplied by cosine theta minus 0.15 sine theta. Okay. So then I'm going to do the first derivative test to find my critical points. So I set this equal to 0. And I know that when I set a fraction equal to 0, all that I really need to be concerned about is the numerator, because 0 divided by anything other than 0 is always going to be 0. So what I really need to do is find out when will this numerator be equal to 0. And then again, since, well, I'll just write this out. And let me change colors here so we can see I'm on to a different step here. So 0 equals negative 0.15 mg times cosine theta minus 0.15 sine theta. Okay, and now divide both sides by the negative 0.15 mg, and I end up with just 0 equals cosine theta minus 0.15 sine theta. So then that gives me that 0.15 sine theta equals cosine theta. And then that gives me 0.15 sine theta over cosine theta equals 1, because remember I'm trying to solve for theta here, so I do need to divide both sides by cosine theta to get all the thetas on one side of the equation. And then I can rewrite this as 0.15 tan theta equals 1. So then that tells me, I'm going to draw a little arrow up here, that tells me that tan theta equals 1 over 0.15. So then I take inverse tan of 1 over 0.15 equals theta, because that's what the inverse function does. It tells me if the input to my original function now becomes the output of the inverse function. And then I go to my handy dandy Desmos for this one, and I find out that that gives me 0.1429 equals theta. So I need to check and see. That I know is a critical point, but I don't know if it's a min or a max. And so that's what I need to check now. And so at theta equals 0.1429, I can check some values lower than that, and I can check some values higher than that to see what will happen. And oops, I made a little typo here. It's not 0.1429, it is 1.1429. Okay, you're probably wondering when I would catch that. So then here now I can check values like 1 and how about 1.5? You know, I know my range is between 0 and pi over 2 because that was given to me back here. But I don't want to use 0 and pi over 2 because that would cause problems with the tangent function. So I'll choose something that's closer to the 1.1429 that's in that interval. And so when I plug in 1 into my derivative here, then I find out that I have a negative value, which means that my original function is decreasing. And when I plug in 1.5 into the derivative function, I get a positive value, which means that my original function is increasing. And I would just do all that right on Desmos. I would just type in the formula for the derivative function and then evaluate that at 1, evaluate it at 1.5, find out it's negative, find out it's positive. That's an easy way to do that. And then now I can see that yes, indeed, right here, I do have a minimum value at 1.1429. That is going to be my minimum value. So let's find out what the minimum force is at that minimum value. So I'm going to need to go to another page here, and I'm going to rewrite my formula here just so I have it in front of me for force. And force is equal to mg mu over, and let me put in the 0.15 because that is what we're working with here. 0.15 mg over sine theta plus 0.15 cosine theta. So I'm going to evaluate f at 1.4219. When I do that on Desmos, I find out that f is equal to 0.1483, and I know that this is a minimum value. So that's the minimum force, the minimum amount of force she needs to move the sled. And then we're asked to find, is there a maximum value? So we also have to look at those endpoints that we were given. We were told that her arm could be at an angle from 0 to pi over 2 from her body. So we'll try f at 0. F at 0 is, now here, you could use a calculator again if you want to, but you don't need to here because you can look and see when f is 0, when theta is 0, sine of 0 is 0. So that term disappears as 0. Cosine of 0 is 1. So I end up with 0.15 mg over 0.15, which is just going to be 1. One mg. Yeah, sorry, I need to put the mg in there. So it's going to be 1 mg. Okay. All right, now let's look at f at pi over 2. f at pi over 2, now again, pi over 2, I'm just going to use what I know about the trig functions. And sine of pi over 2 is 1. Cosine of pi over 2 is 0, so this term would go to 0, and I would have just 0.15 mg over 1, so that would give me 0.15 mg. And so now I can see that, oh yes, this is my minimum value here, and 1 mg is my max value. All right, so I think